Hi everybody, this is Chapter 7, Ionic Bonds and Ionic Compounds. Today we're going to go a step further about ions and now look at how they bond to each other. Okay, this is what used to be called a salt farm. It was taken near the ocean and they made like little patties, like rice patties, and they would then let the water come in and build up these dikes of clay or mud to keep the water in, but the water eventually evaporate, and you can see the big piles of salt that they then got in huge piles with the bulldozer. Okay, so that is sea salt. Okay, other countries we actually mine salt from rocks. This is very common in places like Louisiana, where we have what's called salt domes, and in these salt domes, they actually, after they take the salt out, they actually put oil in it, and that's where our strategic reserve of oil is kept in Louisiana in salt domes, because the salt will not dissolve in oil, and so the oil is very safe there, and it's dry, because what will dissolve in water? The salt. Okay, so that's kind of interesting. Okay, this is an important thing to answer. What is the electrical charge of an ionic compound? You should know this. We're going to talk about this as we go along, but I don't want to keep you in suspense. So let's think about that. For instance, if I have a compound, an ionic compound, which one of them we're going to talk about is sodium chloride. So sodium is like that, and chlorine is like this. So what's going to happen? Chlorine really wants sodium's ion to get an octet. But when it does that, sodium becomes Na+, and chlorine becomes Cl-, right? And what happens, they're attracted to each other and they bond, so you end up getting sodium chloride. Since we have one positive charge and one negative charge, they're going to cancel out in the compound, so our compound is going to be neutral. So compounds are always neutral because the charges of the ions will cancel out, and that's why you'll see some things like, for instance, calcium chloride has a formula like this, meaning we have two chlorides and one calcium. Calcium's in group 2, so it gave 2 electrons to one to each chlorine. So therefore one chlorine got one of the electrons, the other chlorine got the other. So if we look at that, so this one gets this electron and this one gets this electron. Okay? That's how it works. We're going to see that a little bit later too. So an ionic compound is composed of cations and anions that are joined together. As I said, they're electrically neutral. The total positive charge, so if you want a nice definition, the total positive charge is equal to the total negative charge. So we have the total positive charge is equal to the total negative charge. And I showed you that. For instance, sodium chloride, you have +1 and -1. They become 0. In calcium, you had +2, and you had 2 chlorines, and so you had 2 minus charges. I'm going to do it that way. They cancel. So anytime you make a compound, you're going to know it's a stable compound when the charges cancel. So what holds them together? Well, we know that plus is attracted by minus. Okay, so they're called bonds. Okay, so basically that force is like a magnet. The pluses come over and they're attracted to the negatives, and they basically form ionic bonds. So if you have your plus and your minus, they're going to come, okay, and then they form a bond. Okay, and that's because of electrostatic forces. Fancy way of saying the plus and minus are attracted to each other. All right, here's a picture showing how we change the electron configuration. We did this in part 1 of chapter 7. So here we see 3s1. That's this electron here. And this has 3p5. So as I said previously, this electron here wants to go there. So what happens is this becomes 3p6, okay? And we lost the 3s totally. So now we have the noble gas configuration for neon and the noble gas configuration for argon, because the metals go one row lower and the chlorines stay in the same row and go to the other row. I mean, the nonmetals go towards the noble gas in their same row. All right, some other compounds. Aluminum is a metal, and it will react with bromine. Bromine is usually found as Br2, but what happens is the reaction that's shown in the picture, and we get aluminum bromide, okay, which has 3 bromines for every aluminum. Why is that, you might ask? Okay, let's think of where aluminum is on the periodic table. Aluminum is in group 13, so that means aluminum, let's write up here. Aluminum is 3 plus. And we know bromine is in group 17, so it has a minus charge. So if that's the case, we need, that means that this will give up 3 electrons. Okay, but it only gets 1 here, so we need 3 other bromines to do that. Okay, so that's where it comes from. When this loses the 3 electrons, it has to give them 1 to each bromine, because bromine only needs 1 to become bromide. That's why it's going to be Br3. Okay? And that's how we can determine basically what the formula will be for each of these. So a formula is the smallest ratio of the atoms when they combine to balance the nuclear charge. Okay? Now, if you look here, we are using something called formula units. Now, it's very interesting. The reason we came up with this term formula units is we are going to treat it very similar to a molecule. And we'll talk a lot more about molecules when we get to covalent bonding, but we've already talked about them before. Technically, sodium chloride is not a molecule. Okay? It's a formula unit because it represents the simplest ratio. Okay? You won't find in nature 1 sodium and 1 chloride alone. On the other hand, sugar, you will find 1 sugar molecule. So formula units are kind of an artificial construct, okay, so that we can treat ionic compounds like molecules. Now, honestly, the only time we're going to talk about formula units is when you take chemistry classes. Chemists on day-to-day life might call this a molecule, even though that's wrong. It's kind of like weighing and massing things. Chemists will say, I'm going to weigh a sample on the balance. Okay, we're not really weighing, we're massing, but this is kind of the vernacular that we use in common speak. Technically speaking, we should call them formula units. So in other words, you need to know that for the test. All right, so here we go. This is where the idea of formula units comes from. Okay, we already said that sodium has 18 electrons outside normally. When it becomes, I'm sorry, this is chlorine. Chloride will gain 1 electron, so it becomes 18 electrons and only has 17 protons. This is where the minus charge comes. And the sodium ion, of course, has lost that electron, so it has more protons than electrons. Okay? Make sense? All right. Now what happens is, you've seen salt crystals. They're kind of very square. Okay? If you ever really look at salt, you can usually see that with the naked eye. Okay? This is a microscope version, but you can still see it with the naked eye. So what happens is, if we look at the arrangement, chlorine is going to be a little bit bigger. So your purple ones are your sodiums, your chlorines are your green ones. They form this nice cubic shape. Okay? So actually you'll find salt in these nice cubes, but there's lots of sodiums and there's lots of chlorines there. Okay? So it's not like what we saw before, in a molecule where you could have one of each. That's why a formula unit is not this whole thing, but just two of them. So it's the ratio. The ratio in this block is 1 sodium for every chloride. Okay, as I said, the formula unit is the lowest whole number ratio. Okay, just to reiterate that. Now, when we write a formula unit, okay, it's just like anything else. We don't use, okay, when we first do it, okay, here's sodium, here's chloride. So we know we're going to form a bond between them because these two things will cancel out. But when then we write the compound itself, we don't write the charges. Okay, that's the proper way to write the formula. Okay, so now we're going to walk through and make some predictions of how the ratio will exist for compounds of a couple of different elements. Okay, so the first compound is going to be a compound of potassium and oxygen. First thing you can say to yourself, which one's the metal and which one's the nonmetal? Okay, if we look at the periodic table, we'll see that potassium is in group 1, oxygen is in group 16. This is a metal, this is a nonmetal. So this will form a cation, this will form an anion. Okay, so if we look at that, metals always form cations, and oxygens will form anions. And the same here. Magnesium is a metal, so it will form a cation. Nitrogen is a nonmetal, so it will form an anion. Okay, so that's the first thing you're going to think about is which one is going to be the cation and anion. Usually the cation always goes first, so these are in the order that we're going to make our formula in the end too. We know that metals, okay, become cations. They do that by losing valence electrons. And we know that the nonmetals become anions, and so they gain electrons, okay? Enough atoms of each element must be used in the formula so the electrons lost equals the electrons gained, okay? All right, so we have the starting point, what we're going to start with. All right, so we look up potassium. We see potassium's symbol is K. It's in group 1, so it has 1 electron dot. Oxygen is O with 8 electrons around. Not 8. This is wrong. No, it's correct. Okay, it's 6. All right, we got 6 because it's group 16. Okay, notice what they did is they try to show you, here's your 2s, 1, 2, 3, and then 1 p. So these are your p's here. All right, so oxygen needs how many to get 8? If it has 6, it wants a pair here and a pair here. So that means that, guess what? We're going to need an other potassium. So if we look down here, here's 1, here's 2. They're going to give those, let's show you exactly what happens. I'm going to take this one. This one's going to go here. This one's going to go here. And when we do this, K becomes positive. Oxygen now has all 8 electrons, and it has 2 extra ones, 2 minus. Okay? So now we should be able to write the formula. So we have 2 potassium. So we use the subscript to tell us there's 2 potassiums, okay, and 1 oxygen. Okay, so it's a 2 to 1 ratio. Okay, let's go to magnesium now. Okay, here's our electron dots for magnesium and nitrogen. Magnesium's in group 2, so it has 2 electrons. Okay, there's our 2 electrons. Nitrogen's in group 15. There's our 2s and our 3 p's, so it has 5 electrons. Okay, so now we can look at how many it needs. Nitrogen is the anion, and so it wants electrons. It wants 3 electrons to get that. Magnesium can give it 2, right? But we have a problem now. Because when it does that, there still wants 1 more. So if it wants more, we have to add more magnesium. And we keep on adding magnesiums and nitrogens until they balance out. Okay, you could think in your own mind, too, mathematically, that if we have 2 electrons to give and it wants 3, what's the least common multiple? 6. So how many of these will you need to get 6 electrons? We'll need 3 of these, and how many to get 6 electrons? We need, not counting the ones that are already matched, the single ones, we need 2 of these. Okay, let's see if I'm right. All right, so there we go. We've got magnesium, magnesium, magnesium. There's 3 of them, and there's 2 of these. Okay, so if we draw what happens, this will go here, this will go here, and this one will finish this one off. Okay, this one now will go to the second nitrogen. This one will go here. This one will go here. Okay, so all the electrons have been taken care of, and I've showed you where they go. Of course, this becomes 2 plus, and this gained it, so it becomes 3 minus. And so 2, 2, and 2 is plus 6. 3 and 3 is minus 6. They cancel out, so we've got it right. So what are you going to predict? It's going to be Mg subscript 3 and 2. Let's see if we're right. There we go, Mg3 and 2. That's it. Okay. All right, so let's try this one together. We've got calcium reacts with fluorine. Okay. So I'm going to do this one with you. All right, so here's our calcium, 2 electrons. Fluorine only needs 1, so we need 2 fluorines to balance it out. So this goes here, this goes here. This becomes 2 plus, each of these become F minus, so CaF2. Make sense? I hope so. Okay, now let's look at the properties of ionic compounds. They have very special properties that we're going to talk about. Okay, they tend to be crystalline solids at room temperature. Okay, crystalline, you've seen diamonds. Okay, when they're cut nicely, these are all crystals. In the following pages, you'll see some really interesting crystals. Okay, they're going to be arranged in 3-dimensional repeating patterns, and there's several types. We're going to talk about a couple of these types as we go through these pages. It's just for background information. I won't test you on the types. It's something that they really do in freshman chemistry. They don't even do it in AP chemistry that often. All right, so what happens is when they start getting these larger structures, even though we know what the ratios are because of the whole proton-electron structure, since they're near each other, there's going to be a stronger force between them. Okay, there's going to be a larger attractive force than just between 2 of the atoms or 3 of the atoms. So when it builds up like this, we're going to see that the geometry plays a very, very important part. Okay, so they have, as I mentioned, they're crystallized structures, right? And so this means they're solid at room temperature. Actually, they're so strongly held, they don't melt that easily. So they have usually melting points over 1,000 degrees Celsius. I mean, some of them might melt a little bit lower than that, but we're talking much higher than an oven. So you can put salt in an oven and it's not going to melt. Okay, so I think you can answer this question because I mentioned to you about salt domes. So underground, will it be a solid, liquid, or gas? Okay, since it has a high melting point, it's going to be a solid. Okay, so as I said, sodium chloride, 800 degrees C, a little bit less than 1,000 degrees C, over 1,000 degrees Fahrenheit. Now here's a structure of salt arranged in a 3D matrix. Okay, again, the purple are the sodiums, the greens are the chlorides. Now this has, we call this a coordination number of 6 because if we look at this sodium here, it is surrounded by 6 green chloride ions. So it means that if any sodium we go to will be 6. Now let's look at the chloride. Let's look at this chloride here. Okay, this chloride has 1, 2, 3, 4, 5. And since this continues, there would be another one down here. So in terms of coordination number, both for sodium and chlorine, it's going to be 6. Okay. Now, as I was saying, is since it's surrounded by these 6 things, this charge is kind of separated by all these chlorines. But since each one is having 6 other sodiums around it, it gets a net pull of 1. But since it's the geometry of it keeps it nice and structured. Okay, cesium chloride is a little bit different. Okay, it forms this kind of 3D structure where it's surrounded by 8 chlorides. Okay, so this is another type of crystal. Okay, and each crystal has different formations that repeat over and over in the crystal formation. Okay, titanium dioxide. If we look at titanium, is our gray one. Okay, if we look at our gray one here and look at how many red ones, it has 1, 2, 3, 4, 5, 6 red ones. All right. But then if we look at our red, okay, it has 1, 2, and then would have another one here, 3. So actually this one's a good one because you can see it. 1, 2, 3. Okay, so it has 3. So its coordination number for oxygen is 3. That's kind of a weird looking structure. Okay, ionic compounds can conduct electricity or electric current when melted or dissolved in water, but not when they're solid. Okay, so I'm going to do that here for you. Okay, why? Because that structures I just showed you, they're so tightly held, those electrons don't have any place to go. And what is electric current? Electric current is a flow of free electrons. All right, so the electrons and charge has to be free for current to flow. All right, so this is a picture of molten salt. Okay, so it's very, very hot. You can see the picture. It says 801 degrees C to 1,412 degrees C. So it's molten, liquid salt. All right, so we have what's called an anode and a cathode, 2 electrodes there, and we're able to make a current flow through. We can see current flowing in the meter because it will go through the liquid. Okay, because the chlorine will move to the positive electrode, the sodium will move to the negative electrode. And so electricity flows. Now the other thing, since they're good conductor of heat, sometimes they're also good conductors, good conductor of electricity, they're good conductors of heat, okay? So it can hold the heat to generate electricity also. Now if you dissolve it in water, you break down that nice structure and you have freely roaming ions. So that will also conduct electricity because the ions are free to move now in the solution. Okay, this is going to be on your on your play posit. When can an ionic compound conduct electric current? Only when melted or dissolved in water, only when dissolved in water, when solid or melted. Okay, here you go. Answer the question. Ready for the answer? When melted or dissolved in water. Remember, it does not conduct electricity when it's solid. So D would be wrong. And the 2 onlys, you always have to be careful with onlys because that might mean there's other chances for it can be true. All right, to summarize, here are our summary points for this section. Make sure you take a look at these, take them down in your notebook. Same with the definitions. Some more definitions. And the big idea, bonding and interactions. The electrostatic forces between the oppositely charged ions hold the cations and anions together in an ionic compound. Ionic compounds generally have high melting points and can conduct an electric current in solution and in the molten state. All right, that's it, folks. See you next time.